Welcome to Magnetic Minds, a podcast where we unravel the mysteries of electricity, electronics, and everything in between. I'm your host, Professor Vasquez, and today we're diving into Chapter 10 of Principles of Electric Circuits, Conventional Current, Magnetism, and Electromagnetism. So whether you're a student studying circuits or just an electrical curiosity seeker, buckle up because this episode is going to be magnetic, literally. So what is magnetism? Let's start with the basics. What is magnetism? Magnetism is a physical phenomena produced by the motion of electric charges. The magnets attract iron, nickel, or cobalt, but the magic happens at the atomic level. Spinning electrons create tiny magnetic fields. Now, when these tiny fields align, we get a magnet. In electrical circuits, understanding magnetic fields is essential because they're not just passive. They can move things, make sounds, generate electricity, and even store data. Okay, we're zooming in on one of the most fundamental visuals in understanding magnetism, flux lines and magnetic field density. So let's go ahead and break this down. What are magnetic flux lines? So imagine you're drawing the invisible. That's exactly what we do with magnetic flux lines. These lines represent the direction and strength of a magnetic field, and by tradition, they always flow from North Pole to the South Pole by convention. So if you're picturing a bar magnet whose lines arc outward from the north side, they curve around and then re-enter the magnet at the south side, they form this closed loop. It's not just artistic, it's physics. Um, Flux density, what does that line spacing mean? So here's a cool concept for flux density, where those lines are bunched up and hugging each other tight. That's where the magnetic field is strongest. So we say flux density is high. But where those lines spread out and give each other space, that's weaker magnetic field. That's low flux density. So when you look at the slide illustration here, those tight loops around the poles, the power zones, the wide curves farther away, that's where the field fades. And why does this matter? Because flux density isn't just classroom jargon. In transformers, motors, inductors, how tightly magnetic fields are packed determines how much energy can be stored and transferred. So like from an MRI machine to maglev trains, engineers live by this principle. Now that we've talked about magnetic flux lines in theory, let's put our lab coats and bring those invisible forces to life. So magnetic flux lines themselves, totally invisible. You can't see them with your eyes no matter how hard you squint, but the universe gives us a workaround, iron filings. Sprinkle a few of those over a magnetic field and voila, you get a live physical trace of the magnetic field lines. It's like giving shape to the invisible. If you've ever seen the movie The Invisible Man, where they throw that powder on them and all of a sudden they can see the invisible man, that's straightforward, right? Nothing hard here. So in this image, we got two bar magnets, one pair lined north to south, and the other's flipped. So the iron filings trace the field like an artist sketching magnetic contours on canvas of space. So where the filings cluster densely, that's where the magnetic field is strongest. Those are tight, they're high flux regions. Where they thin out, that's low flux, weaker field territory. And so what's beautiful here is how natural this pattern is. The filings don't guess or estimate. They align perfectly with the field, following the same path we discussed before from north to south, looping through space. It's kind of fantastic. It's low tech, but it's high impact. It's a good way to see the field, and it's often one of the first experiments we do in the lab to bridge theory to reality. So remember that this isn't just for show. Understanding how fields behave between multiple magnets helps engineers design magnetic shielding, arrange speaker drivers, and even predict how sensors and robotics will respond. So magnetism may be invisible, but as this slide shows, its footprints are everywhere. Okay, let's talk about magnetic materials and domains in motion. Let's take a look or a peek inside the materials that make magnetism possible, what we call ferromagnetic materials. We're talking about familiar metals here like iron, nickel, cobalt. The what we call the magnetic rock stars of the periodic table. But, well, I call them that. But here's a twist. Even though these materials can become magnets, they don't always start out that way. And why not? It all comes down to the magnetic domains, tiny regions inside the material, each acting like its own little magnet with a little north and south pole. If you take a look at the image on the left, those mini magnets, the domains are all pointing in random directions. North facing left, right, upside down, chaotic. And because they're not aligned, their magnetic effects, they cancel each other out. I think of this, or I relate this to the flow of water. If you've ever gone rafting, that white water rapids where you have that chaotic movement, it's not really moving forward. So you don't have, basically you don't have like laminar flow. You have this turbulence, right? So basically what happens here is you have no net magnetism. The material is unmagnetized, but here's where it does get exciting. When we place that material into an external magnetic field, like from a strong magnet nearby, something pretty amazing happens. All those domains, they start to align, they swing around like compass needles, lining up their poles with the external fields. And that's what you're seeing on the right-hand side of the slide. Now that entire piece of metal behaves like one unified magnet. And that's why you can rub a paper clip with a magnet and turn it temporarily magnetic. The domains inside the clip align with the field you applied. So in electronics, we take full advantage of this domain behavior in transformers, inductors, and even hard disk storage. So where bits of information are written by flipping domains on command. So when someone says a material becomes magnetic, they're really talking about a microscopic alignment, like a party happening inside the atomic lattice. Everyone, imagine, is dancing in their own thing, and all of a sudden a line dance starts, and everyone's moving in the same direction. I don't know if that analogy actually says it clearly or depicts it clearly, but it just popped in my head right now, so yeah. All right, let's talk about measuring the magnetic flux and the quantities that we use to measure magnetic flux, like Tesla. Not the individual, but the unit, Tesla. So we're going to go ahead and shift gears now and talk about numbers. We've been throwing around terms like flux and density. Let's put them into some meaningful mathematical, context that engineers love. So in magnetism, flux represented by that Greek letter phi, that PHI, I might be pronouncing it incorrectly. I may have been pronouncing it incorrectly my entire life. We'll just say phi or phi, either way. It refers to the total number of magnetic lines passing through a surface. So think of it as the magnetic flow crossing an area. Now, how do you quantify that? So we use Weber, or the unit Weber. Capital W, little b is how we abbreviate it. And that's the unit of magnetic flux. It's a fairly large unit, and honestly, we don't toss Webers around lightly. It takes a lot of magnetic field strength to hit just 1 Weber. But what if we want to know how concentrated that magnetic field is? That's where flux density comes in, symbolized by the symbol B or beta. And here's the formula where beta is equal to phi divided by A, where A is the area, so phi divided by area. So B is the flux density. We measure that in Teslas. Phi is the total flux. We measure that in Webers. And A is the area the field lines pass through in square meters. So essentially, flux density tells us how many flux lines are hitting a specific amount of space. Imagine you have a yellow sheet laid out in a magnetic windstorm. And if 100 field lines pierce that sheet in a small space, you've got high flux density. Spread them out over a bigger area, well, that density drops. And what about the Tesla? No, not the car, right? Although it's named after the same genius, 1 Tesla equals 1 Weber per square meter, and it represents a very intense magnetic field. So for reference, Earth's magnetic field is around 50 microtesla. So 1 Tesla is huge in comparison. You'll see Tesla units show up in MRI machines, particularly in research medicine, because those MRI machines are pretty high. The ones for humans are, again, there are MRI machines that we use that are approved for human use, and there are MRI machines that are not approved because we don't know how they're how the magnetic fields yet will interact with tissue, or the biological effects or bioeffects. And so, you'll see some of the higher MRI machines used in primates and stuff. Unfortunately, we experiment with, well, I'm gonna stop. I'm not going to mention that anymore. Other places we see them in particle accelerators, excuse me, magnetic field sensors, places where serious field strength is in play. So when we talk about the power of magnetism, we're not just speaking metaphorically. Math actually brings this home. Okay, the Gauss and Gauss meter. So now that we've explored flux density and Teslas, let's talk about something a bit more down to earth, the Gauss, right? The Tesla, as we saw, is a very large unit. In practical applications, especially in electronics and medical environments, the fields we measure are often much weaker than 1 whole Tesla. So enter the world of Gauss, right? Gauss. So 1 Tesla equals 10,000 Gauss, or to put it differently, 1 Gauss is just 1/10,000th of a Tesla. So when you're working with weaker magnetic fields like those around CRT monitors, low-grade magnets, or even ambient electromagnetic pollution, we're usually dealing in Gauss, not Tesla. Now, look at the image on the slide. That device you see is called a Gauss meter. And it's the go-to tool for measuring magnetic field strength in Gauss. It's showing a reading of 0.002 kilogauss, or 2 Gauss. Not very strong, but strong enough to be useful. So these meters often use a Hall effect sensor. It's a tiny chip that reacts to magnetic fields, and it converts it into a readable voltage. That's what drives a number on the display, and why this is important. Because in engineering, instrumentation, and even safety compliance, you need precise measurements. Whether you're testing magnetic shielding in a speaker cabinet or ensuring your MRI room stays within safe field limits, Gauss meters are essential. And now that you know why they're named that way, it's all about Carl Friedrich Gauss, the mathematician who helped lay the groundwork for electromagnetic field theory. So don't be surprised if you see both units, Teslas for the big stuff, Gauss for everyday, different scales, same principle. Going back to the medical field and discussing the MRIs, when we measure MRIs, you'll hear the terms, it's a 1T MRI, a 2T, 3T, or you'll hear it's a 1 Tesla, 2 Tesla, 3 Tesla MRI machine. 1 Teslas obviously are very older MRI machines and very weak, but that's how you would denote an MRI machine strength. Okay, here we have an example for magnetic quantities. The question is, what is the flux density in a rectangular core that is 8 millimeters by 10 millimeters if the flux is 4.0 milliwebers? So we go back to our formula that beta is equal to phi over area. And then we have the plug and chug basically, but don't forget to do the conversions, right? So B the flux is going to be equal to 4.0 times 10 to the negative 3 Webers. That's how we convert the milliwebers into a number, 10 to the negative 3. And then they give us the area in millimeters. And so the standard units are meters. So make sure you convert the millimeters to meters. So for 8.0, I got to get used to saying 0 instead of O. 8.0 millimeters by 10 millimeters, we convert that, which will be 8.0 times 10 to the negative 3 meters, and then 10 times 10 to the negative 3 meters. Once you've got that into the standard notation there, you can just go ahead and multiply everything out and keep everything in the proper units. And so this will come out too, and don't forget to get your calculator and double check these numbers. 50 Webers per meter squared, or 50 Tesla. Magnetic fields around a wire. So let's move into something a little more dynamic. Magnetic fields don't just come from magnets. They're created every time a current flows through a wire. And the field doesn't just radiate outward. It wraps around the wire in concentric circles. So picture this. You got electricity flowing straight through a wire, and magnetism spiraling around it like a galaxy. So just like the bar magnets, we can actually see this effect using iron filings. So sprinkle them on a sheet, run current through a vertical wire, and those filings will arrange into neat little circles if the current is strong enough. This is more than just some neat visual. It's the foundation of electromagnetism. So every motor, every relay, every solenoid, right, all using this principle. Current creates a magnetic field that can do something. So we'll dive deeper into coiled wires and magnetic amplification in the slides to come. But remember this rule of thumb: no current, no magnetic field. So current flows, magnetism grows. Oh, well, that kind of rhymes. I didn't mean for it to rhyme. Okay, now let's talk about the path of least magnetic resistance. Let's talk about how welcoming a material is to magnetic fields. And this concept is called permeability. It's symbolized by the Greek letter mu. It's like a little fancy U. Permeability measures how easily a magnetic field can pass through a material. So think of it like a magnetic conductivity. The higher the permeability, the easier it is for magnetic field lines to flow. So we measure this in Webers per ampere turn meter, right? And you can see there the units on the slide. It's a bit of a mouthful, but the units capture how field strength relates to current and geometry. So we need a reference point, something universal, and that's where the permeability of a vacuum comes. And we denote that by mu naught, right? Mu, that little sub-zero. It's a constant, and so mu naught is equal to 4 times pi times 10 to the negative 7th Webers per, it's giving ampere turn meter. Again, kind of a bit of a mouthful. So we use this as our baseline. Everything else is compared against it. This leads us to something called relative permeability, and it's symbolized by that little mu sub r. It's dimensionless. It's a dimensionless. It's a dimensionless number, right? So this is just a ratio. Mu sub r is equal to mu over mu naught. So if a material has mu sub r equal to 1, it behaves like a vacuum. If it's 5,000, that's a magnetic superhighway. Iron and its alloys fall into this camp. So understanding permeability is essential when selecting materials for transformer cores, inductors, or shielding, places where magnetic field control is critical. All right, continuing on with magnetic reluctance, the resistance of the magnetic world. If permeability is the ease with which magnetic fields pass through a material, then reluctance is its magnetic resistance. Reluctance, symbolized by that fancy looking R, there it tells us how much a material resists the formation of a magnetic field within it. Remember, these are tiny atomic level magnets. It's kind of like resistance in electrical circuits, but for magnetism. So the formula we see here in the slide, where reluctance is equal to L divided by mu times alpha, where again R is a reluctance in big mouthful ampere turns per Weber. L is just the length of the magnetic path. Mu is the permeability of the material, and again A there is the area or the cross-sectional area. The higher the reluctance, the harder it is for magnetic flux to flow through the material. So thin, long paths with low permeability, high reluctance. Short, fat paths with a high permeability core, low reluctance. Magnetic fields pass through them easily. So when you're designing magnetic circuits like transformer cores or inductors, this formula helps us minimize reluctance to maximize efficiency. Think of reluctance as a magnetic equivalent of friction. It pushes back against the flow of magnetic influence. And again, it might be possible that you will be using these formulas in your work if you're designing these components, or if you're designing something that actually has this phenomenon as part of its as part of the device that you're dealing with. The driving force behind magnetic fields. So we've seen how current generates a magnetic field, but what's the push behind the magnetic field? That push is called magnetomotive force, or MMF. Kind of sounds like World Wrestling Federation, but this is MMF. Wait, what is that? Mixed martial arts? Anyway, I get off topic sometimes. And so MMF, it's the cause of magnetic flux, just like voltage is the cause of electric current. So we use this simple formula, to calculate MMF. F sub m is equal to N times I. So F is the magnetomotive force measured in ampere turns. N is the number of turns of wire in a coil, and I is the current flowing through the wire in amperes. So if you increase the number of turns or the amount of current, you're strengthening the magnetic push. More turns, more force, more current, more flux. This is why tightly wound coils are so effective in motors, transformers, electromagnets, and they imply MMF by stacking turns. So the coil doesn't just shape the field, it amplifies it. Makes you think twice about Magneto in the X-Men, right? What's he doing? Okay, want to know where his power comes from. So you've heard of the movies Ernest Goes to Disneyland, Ernest Goes to the North Pole. Well, here we have our version of Ohm's law goes magnetic, right? You've heard of Ohm's law in electrical circuits. V is equal to I times R. Voltage is equal to current times resistance. Well, magnetic circuits have a version too, and it looks like this. Phi is equal to F sub m divided by reluctance, or divided by R. And here's the analogy. Flux, right? Phi is like current. It's what flows. Magnetomotive force, F sub m, it's like voltage. It causes the flow, and reluctance is like resistance. It opposes the flow. So let's apply it with a quick example from the slide here. And they give you that you have a coil with 300 turns, a current of 100 milliamps, or 0.10 amps, a reluctance of 1.5 times 10 to the negative 7 ampere turns per Weber. Right? And then we can calculate F sub m, which is equal to N sub I. We plug in the numbers. I can say plug and chug the way my old math teacher used to say. 300 times 0.10. And then we end up with 2 microwebers here. So this results in a magnetic flux in the core of 2 microwebers. And this example shows how we can design or evaluate magnetic systems using formulas that mirror what we already know from electrical circuits. It's a magnetic mirror of a familiar theory. All right, continuing with magnetic quantities, the MMF, the magnetic motivator, right? Let's revisit the magnetomotive force, MMF, one more time. This time in the context of a real-world application. So MMF isn't a force in the traditional physics sense. It doesn't push or pull like Newton's forces do. Instead, think of it as the magnetic pressure that drives flux through a material, especially in a core like iron, like the one shown here in the slide. When current flows through a coiled wire wrapped around a magnetic core, it produces a magnetic field. And that field, intensified by the core's properties, becomes concentrated, and it becomes useful for things like transformers, inductors, electromagnetic actuators. So looking at the example here in the slide, we're given that you have 250 turn coil and a 250 turn coil and a current of 3 amps. And if you want to find MMF, you just use that simple formula where F sub m is equal to N times I. And again, plug and chug the numbers, 250 times 3.0, and we end up with 750 ampere turns. So that's 750 ampere turns of magnetomotive force pushing magnetic flux through the iron core. And think about it again, more turns, more current, that equals more MMF, that equals more flux. It's simple, elegant, and incredibly useful. Okay, let's go on to solenoids, from current to motion. Let's finish this part of the lecture with the real world marvel, which is the solenoid. So a solenoid is where everything we've learned about magnetism gets practical. It's a device that converts an electrical signal to a mechanical motion, and here's how it works. So you send current through the coil, a tightly wound wire, and that current generates a magnetic field. That field pulls a sliding core or a plunger inside the coil. A spring usually resets the plunger when the current stops. And that simple back and forth motion, well, it powers door locks, pinball flippers, fuel injectors. In the diagram, you see a common application, a valve that controls fluid in a pipe. That's used in something like a sprinkler system or dishwashers or even a car transmission. The solenoid is one of the most direct and elegant demonstrations of electromagnetic energy being turned into motion. There's no magic, just magnetism at work. And that, students, brings us to magnetic quantities, or it brings a close to the magnetic quantities, right? From flux lines to field strength, from reluctance to real-world applications, you now have a basic foundation to understand how magnetism shapes our modern world and literally moves it. All right, let's get into the summary here. The magnetic middleman, right? So now that we've seen how solenoids convert electrical signals into motion, let's take a look at another workhorse of electromagnetic control, which is the relay. A relay is essentially a magnetically controlled switch. Think of it as a way to use a small control voltage to manage a much larger current. So without the two ever physically touching or meeting, except through the electromagnetic field. So when current flows through the relay's coil, it generates a magnetic field. That field pulls a movable contact, which switches the connection between two terminals. And so the slide here shows a common schematic for this. You see CR1, this is the coil symbol. NC means normally closed, so current flows when the relay is off. And NO means normally open, so current flows when the relay is on. The movable contact shifts between them based on whether the coil is energized. So relays are the backbone of automation. You'll find them in automotive electronics, industrial control panels, even inside your washing machines. They give systems the power to decide to switch circuits on or off based on logic, safety, or timing. So the next time you hear some soft click inside a control box, you'll know what that is. That's a relay doing its job, silently making decisions with the help of magnetism. Let's talk about how hard a current has to work to set up a magnetic field. And that concept is called magnetic field intensity, symbolized by the symbol H, or the letter H. Think of it like this. If flux density tells us how much magnetic field is present, field intensity tells us how much work it took to make it happen per unit length of the magnetic path. And the formula is pretty straightforward here on the slide. H is equal to F sub m divided by L, or also H is equal to N times I divided by L. So where H is a magnetic field intensity, and we measure that again in ampere turns per meter. F sub m is the magnetomotive force. L is the average length of the magnetic path. N is the number of turns in the coil, and again, I is the current. So the longer the path or the weaker the coil, the more effort it takes to generate a certain flux density. And this concept it's vital when designing transformers or magnetic circuits where material geometry and energy efficiency matter. You're not just choosing materials, you're budgeting for effort. So here, let's talk about magnetic saturation. So where more doesn't mean stronger, right? To close out our discussion on magnetic quantities, let's connect two key ideas. The first is flux density, right, denoted by B, and magnetic field intensity denoted by H. And the relationship between them is B is equal to mu times H, where mu is a material's permeability, if you remember that. H is the magnetic field intensity, and B is the resulting flux density. What this tells us is the more effort, or H, you apply, the more flux, or B, that you create, as long as the material can handle it. There's always a real, world practical limit to these things. But here's the catch. Every material has its limit, and that limit is called saturation. And at some point, increasing H further doesn't increase B, so the magnetic domains are all aligned, the material is fully magnetized, and no extra push is going to help. So at some point, increasing H further doesn't increase beta. So imagine trying to fill a sponge with water. It works up to a point, then it just drips, and that's saturation. So when designing magnetic systems, you have to choose materials with a permeability that suits your needs and stay below saturation if you want predictable results. All right, so motion sparks voltage, the magic of electromagnetic induction. So let's talk about one of the most important ideas in electromagnetism, which is relative motion. If you've got a wire and a magnetic field and one moves past the other, something really fascinating happens. Voltage is induced in the wire. Now here's a catch. It doesn't matter which one moves. So move the wire through the stationary magnetic field, you get an induced voltage. Move the magnet past a stationary wire, you get the same result. So in both cases, what matters is relative motion between the two. It's this principle that powers generators and wind turbines. Even the way our bikes light up with, I don't know if any of you had those dynamos back in the 70s where you put them on your bicycle and you would convert your mechanical energy into electrical energy to light up a bulb so you can see your way at night. Well, I had one of those, and that thing was difficult to pedal once you engaged it. So it's kind of better just not to have the light. But here the slide shows a simple setup where a wire slices through magnetic field lines. And this motion cuts across those invisible lines, disturbing the magnetic field just enough to generate a current. So remember that motion and magnetism equal electricity, and then that's electromagnetic induction in a nutshell, and it's the foundation of how we generate nearly all the electricity in the world. Okay, so this slide reminds me of a scene from a movie, The Princess Bride. Believe to believe, which was, I forgot what they said in the movie. Anyway, B, L, and V, the equation that lights up the world. So let's get quantitative here. Now that we know relative motion between a wire and a magnetic field induces a voltage, let's figure out how much. The formula for induced voltage when the motion is perpendicular to the magnetic field is shown here in the slide. V induced is equal to B times L times V, where B is the magnetic flux density, that's in Teslas. L is the length of the conductor in meters within the magnetic field, and V is velocity. So how fast a wire or field is moving in meters per second. And this is a pretty elegant equation. Take how strong the field is, how long the wire is in the field, and how fast it's cutting across the field, and you get the voltage that's induced. This principle is exactly what makes generators, alternators, and even dynamos to work. I shouldn't say even dynamos. I have a negative bias against dynamos just because of my bicycle incident. You move coils or magnets and then energy flows. And remember, this only works when the motion is perpendicular to the field. You have no perpendicular motion, no voltage. It's the slicing that matters. So BLV, simple letters, world-changing impact. Faraday's law, right? Again, the spark that changed the world. So if there's one name you should associate with electromagnetic induction, it's Michael Faraday. Faraday was the pioneer who discovered what moving a magnet near a coil of wire could generate. It could generate electric current. And again, not by contact, but by changing magnetic field conditions. I've seen several documentaries on his work, and he has such an interesting life, but I won't go into that now. But the key insight, it's not the magnet itself that causes voltage, it's the movement. So what we see here in this slide is an introduction to the first factor in Faraday's law, the rate of change of magnetic flux with respect to the coil. So in simpler terms, how quickly the magnetic environment is changing around the coil determines how much voltage is produced. If the magnet moves slowly, the change is small, right? So you get low voltage. Move it quickly, the change is rapid, you get more voltage. And here's something very crucial. If the magnet just sits there, even if it's strong, no voltage is induced. So motion is mandatory. If you look at the animation here on this slide, or at least the perceived animation here, and again, you have to use your imagination for this. A bar magnet sliding in and out of a coil with a voltmeter needle dancing only while the magnet moves. This is a principle behind electric generators and even guitar pickups, right? So no change in flux, no electricity. All right, let's continue with Faraday's law, right? So twist the coil, boost the power. We've learned that changing magnetic flux near a coil induces voltage, but Faraday didn't stop there. He found that the amount of wire in the coil, the number of turns, makes a big difference too. So that brings us to the second factor in Faraday's law, the number of turns of a wire in the coil. The more turns you have, the more loops the magnetic field interacts with, and the more voltage that gets induced. So let's say you're sliding a magnet through a single loop. maybe you get 1 volt. But if you slide it through a 10-turn coil at the same speed, you get 10 volts. So in the slide, we see a multi-turn coil around the same magnet. Oh, and don't take those numbers that I said as fact. That's just using numbers as a way for you to imagine the amplification. So the effect ends up that the voltmeter spikes higher. So the induced voltage isn't just about how fast the magnetic field changes, it's also about how many coils are listening. And if you want to summarize all this, the faster change in flux, you get more voltage. More coil turns, you get more voltage. And again, if the magnet's not moving, nothing happens. Again, movement is everything. So this principle is what allows power plants to scale up energy generation. So more windings, more flux, more electricity. Let's talk about the coil as a magnet, right? Electromagnetism in action. So up until now, you know that moving magnets can create current in a wire, but what if we flip the script? Current can also create a magnetic field. So current flows through a coil of wire, it produces a magnetic field that looks just like the field of a bar magnet with a distinct north and a south pole. And that's what we call an electromagnet. So this slide here illustrates this beautifully. The battery supplies current, the coil wraps the wire into tight loops, and the resulting magnetic field loops outward from one end and returns to the other, and that forms those classic field lines. The coil doesn't just act like a magnet, it becomes one. And what's more, it's a magnet you can turn on and off with a switch. And this is a foundation for devices like electric motors, magnetic locks, even MRI machines, and even the humble doorbell that you most likely have at your home. Unless you got a Ring doorbell, right? Not sure what that looks like on the inside. But motion can induce current, and current can induce motion, all thanks to the dance between the coils and the magnetic fields. A dance. Not much, not unlike a tango. All right, the DC motor, right, turning electricity into motion. Let's bring everything full circle, and I mean literally. All this talk of magnetic fields, coils, and current leads us to one of the most practical applications in electronics, and that's the DC motor. And so let's discuss a little bit of how it works. You have a coil of wire, and we call that the armature, and that sits in a magnetic field between a north and a south pole. So when current flows through the coil, it creates a magnetic field of its own, and this new field interacts with the fixed magnet's field. And this generates a rotational force or a torque. But there's a twist. And again, I mean that literally. To keep the motor spinning, the direction of the current needs to reverse every half turn. So that's where the commutator comes in. It's a split ring connected to the coil and touches brushes that bring in the current. So as the motor turns, the commutator flips the current at just the right moment, keeping the torque in the same direction, and the motor starts spinning smoothly or smoother. Right? In small DC motors like the one illustrated here on the slide, the magnet is fixed and the armature rotates. It's a design used in small toys, tools, fans. And so what do we have? We have electricity coming in, magnetism is created, motion is a result, and that's electromagnetic engineering in motion, right? Literally powering the modern world. Continuing with the brushless DC motor, the silent revolution. In this circuit, in this modern marvel, the brushless DC motor, or BLDC, right? While traditional DC motors use brushes and commutators to switch current direction, brushless motors, they skip the mechanical contact altogether. Instead, they rely on an electronic controller, and it smartly reverses the current in the stator windings, and this is how it works. So you have the stator, which is a stationary coil, and it's powered by the controller. The controller switches current in these coils at just the right time to create a rotating magnetic field. You have the rotor, which is a permanent magnet, it follows the rotating field spinning along. So you get no friction, no wear from brushes, just clean, efficient rotation. And this cutaway that you see here in the slide, what are the things you can spot? Well, the first is the Hall sensor. It detects rotor position so that the controller knows exactly when to switch fields. You have the stator and the permanent magnet rotor. That's the core working pair. The shaft, where the mechanical energy exits to do the work. So brushless motors are used in drones, electric cars, hard drives, anywhere you want quiet, efficient, and durable motion. And that's kind of like the big takeaway. We've gone from inducing voltage with motion to creating motion with current, and now to controlling that motion electronically. And it's a full cycle of electromagnetic mastery by the engineer. We are the masters of the electron, which in turn indirectly controls the magnetic fields. So magnetic units, and this is your final field guide. So before we close the book on magnetism, or the chapter, let's run through a quick reference here. As you see on the table, I actually won't go through the entire table. You can I'll go through some of them, some of the key quantities or symbols and the units. And think of this as your cheat sheet for solving problems and reading schematics. So again, we've covered all of these. Magnetic field intensity, the symbol is H, the unit is ampere turns per meter, and the symbol is capital A, little t divided by m. Right? Magnetic flux is, the symbol is phi, the unit is called a Weber, and again the symbol is capital W, little b. I won't read the rest, you can kind of go through that on your own. But before I finish off this slide, I want to say that's it. With these magnetic units in your toolbox, you're officially equipped to navigate the invisible but mighty world of electromagnetism. Again, thank you very much for your time. I'm going to go ahead and review some terminology before we end with this lecture. And so, thank you very much. Stay curious, stay charged, stay current. And that was a pun intended. Okay, so I'm going to go ahead and just do a quick review of the key terms that we learned in this lecture. And I'm just going to be reading off the slides. You can just follow along, or you can just look away, relax, and listen to me read the definitions for you. Right, so the magnetic field is a force field radiating from the North Pole to the South Pole of a magnet. Magnetic flux, the lines of force between the North Pole and South Pole of a permanent magnet or an electromagnet. A Weber, designated by capital W, little b, the SI unit of magnetic flux, with it represents 10 to the 8th lines, excuse me. Permeability, the measure of ease with which a magnetic field can be established in a material. Reluctance, the opposition to the establishment of a magnetic field in a material. I'll continue with more definitions on the next slide. Continuing, magnetomotive force, MMF, the cause of a magnetic field measured in ampere turns, denoted by capital A, little t. Solenoid, an electromagnetically controlled device in which the mechanical movement of a shaft or plunger is activated by a magnetizing current. Hysteresis, we didn't talk about this in the slides, so I'm glad I'm reading these now. A characteristic of a magnetic material whereby a change in magnetism lags the application of the magnetic field intensity. Every time we talk about hysteresis, we're talking about a change. It's due to a change in something, or a rate of change in something. Retentivity, it's another term we didn't actually mention in the presentation. The ability of a material, once magnetized, to maintain a magnetized state without the presence of a magnetizing current. And to conclude our selected key terms, we have induced voltage, symbolized by little v and in sub ind for induced. Voltage produced as a result of a changing magnetic field. Faraday's law, a law stating that the voltage induced across a coil of wire equals the number of turns in the coil times the rate of change of the magnetic flux. And the last key term for this lesson is Lenz's law. Now, we haven't actually discussed Lenz's law, but we will in future presentations. A law stating that when the current through a coil changes, the polarity of the induced voltage created by the changing magnetic field is such that it always opposes the change in the current that caused it. The current cannot change instantaneously. All right, I want to thank you for the lecture, and the next thing we're going to be going over is a small review quiz. So the first question on our review quiz here is, a unit of flux density that is the same as a Weber per meter squared is the what? Ampere turn per Weber, ampere turn per meter, or a Tesla? Go ahead and pause it now and think about the answer, and I'll tell the answer in a second. Okay, so hopefully you paused, and the answer is D, a Tesla. Question number 2. If one magnetic circuit has a larger flux than a second magnetic circuit, then the first circuit has what? A higher flux density, the same flux density, a lower flux density. Answer depends on the particular circuit. Okay, again, pause for a few seconds, answer, and then turn it back on. All right, hopefully you paused. And the answer for this one is D. Answer depends on the particular circuit. Question number 3. The cause of magnetic flux is A, magnetomotive force, B, induced voltage, C, induced current, or D, hysteresis. Pause and come back. And the answer here is A, magnetomotive force. Question number 4. The measurement unit for permeability is A, Webers per ampere turn, B, ampere turn per Weber, C, Weber per ampere turn meter, or D, dimensionless. Pause. Come back. And the correct answer is C, Weber per ampere turn meter. Question number 5. The measurement unit for relative permeability is A, Weber per ampere turn, B, ampere turn per Weber, C, Weber per ampere turn meter, or D, dimensionless. Pause for a moment. All right, come back. And the answer is it's dimensionless, which is D. Sorry. Question number 6. The property of a magnetic material to behave as if it had a memory is called A, remembrance, B, hysteresis, C, reluctance, or D, permittivity. All right, go ahead and pause for a second. And the correct answer here is B, hysteresis. Question number 7, and for the sake of time, I won't read all the variables for the equations. Ohm's law for a magnetic circuit is A, B, C, or D. Pause, come back, and the correct answer is C, right? Phi is equal to F sub m divided by R. Question number 8. The control voltage for a relay is applied to the A, normally open contacts, B, normally closed contacts, C, the coil, or D, the armature. Go ahead and pause. All right, come back. And the correct answer was C, the coil. Question number 9. A partial hysteresis curve is shown. At the point indicated, magnetic flux is what? A is 0, B exists with no magnetizing force, C is maximum, or D is proportional to the current. Again, go ahead and pause. All right, come back. And the correct answer here was B, exists with no magnetizing force. And question number 10. When the current through a coil changes, the induced voltage across the coil will what? A, oppose the change in the current that caused it. B, add to the change in the current that caused it. C, be zero. Or D, be equal to the source voltage. Pause for a second. All right, come back. And the correct answer is A, oppose the change in the current that caused it. All right, I want to thank you because that's the last question of our quiz self-assessment. Go ahead and check your answers with the slides, the following slides, and I want to thank you very much for sticking it out through this entire lecture. I will see you in the next one.